All right, guys, so this is problem 6-2. So previous to this, we've done problems where we have a steady B field, like the B field is not changing, but then we have a loop and we're moving it through the B field. In this case, this is a little different where this circuit is not moving, it's staying in place. But this B field that's coming through the center of the circuit is actually changing with respect to time. So this is a fluctuating B field. So when we have this changing B field, okay, even though this circuit is not moving with any kind of velocity, it's still going to induce a voltage and a current through that loop. So whether the change in the fluctuation in the B field is due to the fact that we are physically moving through it or the B field itself is moving, the result is essentially the same. Okay, so this equation, what we're going to do, we have our expression for B, okay? And then we are going to find this ds. So what this ds is we are going to take the entire surface area of the circuit that the B field is coming through. So we're just treating this surface area like a square, okay? So in this case, we have the z direction and the y direction, because those are the coordinates that were given. So we have the change with respect to z, so dz multiplied by dy, right? And then our direction normal to this surface is the x hat direction, so normal to coming up at a right angle, okay? Then for this one, we're actually going to sub out our dz value because it's static, so 0.1 right over here we can see is our value for the z direction. But we're not going to sub out our y because if we notice for our B field expression, we have a y in here. So B is a function of y, so we're going to leave this in, and we're going to integrate and then just bound from 0 to 0.3, okay? So let's plug in our components. So we're going to plug in the B field that we're given up here, so that B field is in the x hat direction, okay? And then our ds is also in the x hat direction, okay? So then we're dotting these together, so x hat dot x hat equals 1, and then we're just pulling kind of some constants out to the outside here. And just moving our integral over. Okay, so taking the derivative as a function of, or integrating as with dy here, we're going to do the tricky part about this problem. I won't go super into the math. I'm just going to kind of point to it and then let you guys solve this one out on your own. But we're doing a u sub here for the center part of this. So just taking u to be equal to this, if we take the derivative of this piece, we're going to end up with negative 1/3 pi dy, and then we just are dividing this du to on this side to give us our dy. So then essentially what we're doing is we're subbing out dy, right, for this value of du, just to get our constant multiplier, and then we're subbing out this piece for u, okay? So we can integrate, right, and then essentially we want to plug our u value back in, and then we can evaluate the bounds, okay? So not super crazy, but it's a little bit finicky. So just go ahead and kind of take a look at that. So, okay, so just some more math here and simplifying and just kind of pulling our constants out to the outside. And then after we do that, we are going to, and we also are plugging in the bounds here. So plugging in, so we have y is equal to 0.3 and then y is equal to 0. And then we get this piece minus this piece. So first bound, so top bound, bottom bound. And then we're taking the derivative with respect to time. So when we take the derivative of a trig function, we're basically multiplying by this guy here, right? Because that's the only t value on the inside. This piece is the constant. So the expression for both of these, it's going to turn into cosine. Sine will turn into cosine, and then it's multiplied by this guy. Okay, so essentially we get our full value for the EMF, and then to find our current, all we need to do is divide by the total resistance in the circuit. So again, this is just Ohm's law here, V equals IR, just rearranged a little bit to get our current. So divide our EMF voltage by the total resistance, okay? And then we can end up with our current expression. So you could simplify this a little bit more, but this is okay. So yeah, so just to reiterate for this one, the difference that we see this in this problem compared to our other problems is that this loop is staying in one place and the B field is what is fluctuating. So we're taking, we're integrating our B field through the surface of the circuit and then taking with the bounds for the surface, and then we're taking the derivative with respect to time.